We have two types of particles that we collide in a collider. On the one hand, it's protons, which are composite particles, very heavy. So they are like the particles we use in the LHC, and they allow us to reach very high energies. And then we have electrons and positrons, which are antiparticles, which are point-like. So they are sort of all of the energies in one single point, which we can also collide, like in the accelerator that we had in the LHC tunnel before lab. Now the problem with increasing the energies of electron-positron colliders is that if you force the particles on a circular orbit, as you have to do for a collider, you get very large amounts of synchrotron radiation. So now the solution is you can make the collider very big, but it becomes very expensive and it doesn't give you much more energy. Or you can look for other particles to collide, which are muons. They are like electrons and positrons. They are much heavier, so they emit much less synchrotron radiation, which is great.
What it does do, the Muon Collider, is give us a path to multi-TeV energies in a relatively small footprint.
The Muon Collider has some linear parts and then a booster ring and a collider ring, but it's roughly the size of LHC. That's what we are talking about. It's not anything much beyond what we have done already for accelerator, and that's why that's one of the main reasons why I think it's interesting. It's a fairly compact machine, and there are other more technical reasons. We think that maybe the power consumption of the machine is quite reasonable, which is going to be extremely important given the energy prices and given the sustainability frameworks which we have to work within for future facilities. For the Higgs factory, they operate at 400 GeV, and you do that with electrons and positrons, and that's what you need to produce a lot of Higgses. And this is what is foreseen for FCCEE or for CLIC or for ILC and for all these options. They have all in that energy range. The Muon Collider, which collide muons, aim to go to 10 TeV, so more than a factor 20 higher than the Higgs factories. So much higher energies. And this we really don't know any other way to do that with either electrons or any other lepton. So we have to do that with muons.
The near-term goal is within 4 or 5 years to show that actually this looks promising enough to invest into a real development program. So a demonstrator, which would be a small facility to demonstrate the main technologies of this collider, then individual components, and to do a CDR, so a conceptual design report, which means a report that describes how the Muon Collider would function. It gives the fundamental technology descriptions and the specifications for components, and also a cost estimate. So that's the near-term goal for the next few years. If that is successful, we would actually have to build a demonstrator to show that it really works as we promised. And after that, one could launch into a technical design.
Muons at 10 TeV is really very competitive to a 100 TeV hadron machine. In many areas you need technology development, and that's one of, and many parts of this technology is relevant to be used in industry, medical systems, or for other type of accelerator. So this is one of the reasons why the Muon Collider studies are in a way popular in the accelerator community, because it has many different challenges which are also relevant for other parts of society and for other type of science.
My name is Carrie DiPetrillo. I come from the United States, where I'm a postdoc at Fermilab. So one of the main reasons that I'm interested in a Muon Collider is because it's, I think, our best hope to have a discovery machine in my lifetime. In 20 years or so, I hope to be a senior professor in particle physics. I hope to be a leader in the field. And the high luminosity LHC will be coming to an end. And I hope that we have a new collider coming up soon after that. And I think Muon Colliders are predicted to have a 20-year technically limited timeline to first physics. And it's really the best hope for a discovery machine in my lifetime.
Europe needs a flagship machine. It's clear. CERN, if we want to secure the future post high luminosity LHC, we're looking towards a big project to carry on using our established expertise and facilities. If the FCC isn't approved, then the Muon Collider would provide a very interesting alternative.